In this video, we'll begin discussion of the limits of trigonometric functions. So the kind of problem that we're going to be dealing with is something of this sort. Let's say that we have a limit as x approaches 0 of some trig function like that. And the reason that we're going to want to do this is in order to start figuring out what the derivative of trig functions are and to do all the kind of calculus that we've done before just with this new class of function, the trig functions. Now, the good news with the trig functions is that they behave quite nicely, and so the taking limits for the most part amounts to just plugging in the number. So this is perhaps not too surprisingly the same. And so the piece on the inside is easy. The limit as x goes to 0 of 7x is just 0. And so we should guess that this is just sine of 0, which is 0. Now a geometric way to sort of view it is, so let me draw a set of coordinate axes. So I'll do just the positive x-axis here. And I'll do the sine curve in blue, so it'll be something like this. And then it'll keep going, of course. So and then let me graph it a little bit in the negative direction too. Okay, so it'll keep going like that. So what we're asking is, what happens to the y values as the x values are getting close to 0? And pretty easily from the graph we can see that it looks like the y values are also going to be 0, my picture notwithstanding, and so we would guess that the limit is 0. And in fact it is 0 because of this kind of computation. And the reason that I'm allowed to just slip the limit inside like that is because sine of x is a continuous function. In fact, all the trig functions are continuous, provided that they're defined. So all trig functions are continuous on their domains. And that part's really important because, say, something like tangent, it's not even defined at x equals pi halves, and so it can't possibly be continuous. But anyway they're defined, you can always do this sort of trick. Okay, so let's take another sort of similar example. Let's take limit as x goes to pi of sine of 7x. So the same idea works here. This should just be sine of the limit. And as x approaches pi, this approaches 7 pi. And then we just have to think a little bit about our unit circle, that 7 pi is just a whole number multiple of pi, and sine is 0 at all of those, so this one is in fact also 0. So let's do a different one. Let's say that we had the limit as x goes to something like, I don't know, let's say 5 pi over 4 of sine of 7x. Then we'd plug that in, and so we'd get sine of, well, it'd be what, 35 pi over 4. And then we just have to think about, well, which quadrant is this in, and so on. So it's going to be square root of 2 over 2. The question is whether or not we need a minus in front. So we just have to kind of count. 35 divided by 4, well, 36 over 4 is, what, 9. And so this one is just shy of 8 full 4 pi increments. Or you could just kind of count it. So like if we have got the unit circle, here's 1 pi, 2 pi, 3 pi, 4 pi, or in pi fourths, because what we're dealing with here, it'd be 4 pi fourths, 8, 12, 16, then 20, 24, 28, 32, and then this one would be 36, but we've only got 35, and that means that we're right here. So in fact, this is just the same as pi force, and so we'd say its reference angle is pi force, and so we have the plus one here instead of the minus. But essentially what this comes down to, at least for right now, is that if the function is nice, you're allowed to just plug it in. Now in class we'll look at slightly more complicated problems where like plugging in might give us a 0 over 0 kind of situation, and in those kind of cases we need to be much more careful.